In this segment, we're going to talk about how we can use the fundamental theorem of line integrals to draw a conclusion about integration over a closed curve for a conservative vector field. All right, so let C be a closed curve from A to B. And that would mean that point A must equal point B. Okay, so let's draw a picture here. All right. So maybe our curve looks something like this. There we go. This would be our point, which is going to represent what's going on here. Okay, this would represent both A and B. And let's just give our curve an orientation. Okay. Okay. So a closed curve is a curve that starts and ends at the same point as I've drawn. Okay, so if F is conservative, so that means that the vector field F must equal the gradient of some potential function little f, and C is a closed curve, then the line integral over C of f dot dr must equal 0. So why is that? So if you think about the fundamental theorem of line integrals, well, we have the line integral over C of f dot dr. Well, that must equal the line integral over C of gradient little f dot dr, because we're making the assumption that F is a conservative vector field and therefore must equal the gradient of some potential little f. Well, when we integrate gradient f, we're going to get little f of b minus little f of a. But for a closed curve, a equals b, therefore little f of b minus little f of a equals 0. Okay, so remember what the physical interpretation of a line integral of a vector field is? The line integral over C of f dot dr is the work done as you move along the curve C. So what we're saying in this case is that the work done along a closed curve of is 0. Okay, the work done along a closed curve, if the vector field is conservative, is 0. And again, that word conservative has to do with conservation of energy. All right, so let's think of this in a more practical way here. Let's see. Okay, so let's let F be the gravitational field, okay? So F is the gravitational field. Okay, so here I'll draw a picture of a closed curve C. And, okay, here's my curve. Here's my point A, B. Okay, and so let's imagine our closed curve is a a road where we're going to ride along this road, and we're going to start at and end at the same point. Our road is a loop. And let's draw a picture of a vector field, and maybe my vector field looks something like this. So this is C, and this is vector field F. Okay. And let's say that you get on your bicycle and you ride along this curve, okay? And maybe you ride over to this point on the curve, and you're riding to work. And if you remember, we talked about how if the vector field is pointing in roughly the same direction as the tangent vectors along curve C, then that gives a positive inner product, okay? So we're riding our bicycle along C, and the integral over C always has a positive inner product with the velocity vector in this picture because they are pointing in the same direction. So that dot product will have a positive value. So, in other words, as we ride our bicycle along curve C, the gravitational field is helping us, right? It's pushing us along the road, so we don't really need to pedal that hard, if at all. So let's say, here we go, we're riding to work, and I'm riding along curve C, and look at this, I'm riding all the way downhill to work. Well, let's say I don't want to go back home the same way. Let's say I continue along curve C and I complete the loop to go back home. Well, so now I'm riding downhill all the way back home, and I'm still arriving back at the starting point. Well, obviously, this is not possible in reality, right? In this picture, in this diagram, the integral over C of f dot dr, remember that would have a positive value. And that would tell me that this vector field F is not conservative. Well, this is not possible in reality because of conservation of energy. So in reality, our gravitational field could not look like this.